Welcome to today's lecture on material balance calculations for single unit systems with reactions. So, to start with, we have now understood the fundamentals associated with reactive processes and the terminologies which will be used when we discuss processes having reactions and reactors. So, we will start off with the simplest possible systems which have reactions, which are single unit systems containing only a single reaction. What we will do is, we will first try to understand what a reactor is, and we will look at the different ways we can write balance equations for this type of a system. What is a reactor? The diagram you see here is a typical representation of a reactor which has two feeds and a recycle. You can have products which could be gas products or liquid products or solid products. These products could be coming out as different streams and they can actually be separated further. Consider this reaction which is shown here. You have ethane forming ethylene and hydrogen. So, the reaction system is given as 100 kilomoles of ethane entering per minute reacting to form 40 kilomoles of hydrogen per minute. We do not know the number of moles of ethane and ethylene which are leaving the system. Now that we have this system, what kind of balances can we write? When we looked at water conserved, we identified that the mass of the total substance and the mass of individual components would be conserved. So, we can write the total balance, which is the total mass balance, and we can also write individual component balances, which would be the ethane, ethylene and hydrogen balances. Let us see how these equations would look and how we can solve for N1 and N2. So, we now have the reaction system and we can write the total mass balance. Before that, we need to identify the basis for the system. For the given conditions, you have 100 kilomoles of ethane entering, which means the basis would be 100 kilomoles of ethane per minute. Now, the total mass balance should be written in terms of masses, not in terms of moles, as we already looked at. Mass is conserved, number of moles is not conserved during a reaction. So, the total mass would be written as 100 kilomoles of ethane times the molecular weight of ethane, which is 30, is the input mass, and you have the output mass as 40 times 2 representing the mass of hydrogen leaving the system, and N1 times 30 representing the mass of ethane leaving the system, and N2 times 28 which is the mass of ethylene leaving the system. Now, we can also write ethane and ethylene balances. Ethane balance is 100 moles entering and this is equal to N1 moles which is leaving plus consumption. So, this equation basically comes down from input minus output plus generation minus consumption equals accumulation. Assuming steady state, accumulation goes to 0. Now, we have an input term for ethane because we know 100 kilomoles of ethane is entering. There is also an output term because we know that N1 kilomoles of ethane is leaving the system. Is there a generation term? No, because this is a reactant. So, the generation term goes to 0. However, we still have a consumption term. So, this means the equation comes down to input equals output plus consumption, which is what we have written here, which is N1 plus consumption. For ethylene, the equation comes down to input minus output plus generation minus consumption equals accumulation, accumulation going to 0 because of steady state, and there is no consumption because this is a product which is only being produced. You do not have any input. This implies you have output equals generation, which is what we have written as generation equals N2, which is the output. Similarly, for hydrogen, we can write the balance equation as generation equals output, which is 40 kilomoles per minute. One thing you would have observed is, when I wrote the total mass balance, I had converted all the moles to masses. However, when I wrote the individual component balances, I did not bother to convert the moles to masses. Why? The reason is simple. You would actually be multiplying all these moles by molecular weight to convert them to masses. So, each of these terms would be multiplied by the molecular weight of the particular component, which can get cancelled off. This would lead to finally the same equation. So, that is why we did not have to convert it to mass for individual components. Now that we have 3 equations, we can easily solve for the 2 unknowns and we will be able to get the final value. So, we can actually use stoichiometry to know that for every mole of hydrogen produced, you would have 1 mole of ethylene also being produced. So, using that you can identify the generation of ethylene and that will give you the output of ethylene, which is N2, and similarly you can know the consumption of ethane using the stoichiometry. So, 1 mole of ethane consumed results in the formation of 1 mole of hydrogen. So, which means 40 moles of ethane has to be consumed to produce 40 moles of hydrogen. So, substituting that we would be able to get the value for N1 also. So, using stoichiometry and these balances we can actually calculate N1 and N2. Other than these molecular species balances, what other balances can we write? If you remember the fundamentals which we covered for reactive processes, we thought that other than mass, the number of atoms of individual elements are also conserved, which means we can write atomic balances. For this particular system, we have carbon and hydrogen atoms which are present, and the balance for carbon and hydrogen atoms can be written. Let us see how we would go about doing that. So, first thing we need to understand is atoms can neither be created nor be destroyed in a chemical reaction. That is why the number of atoms of carbon in the reactant is the same as the number of atoms of carbon in your product. So, this implies generation and consumption terms will be always 0 for atomic species balances. As we always assume steady state, accumulation will also be 0. So, the equation simplifies to input equals output. Now, let us look at the same example problem and see whether we can write atomic species balances and arrive at the same answers. Carbon balance would look like this. You have 100 kilomoles of carbon entering, we will be multiplying that with 2, because with each mole of ethane entering, 2 atoms of carbon is also entering. So, for each molecule of ethane you have 2 atoms of carbon. So, when we convert 100 kilomoles of ethane, we would actually have 100 times 2 kilomoles of carbon entering the system. So, that is your input, and your output would be carbon leaving through ethane and ethylene, and both ethane and ethylene have 2 atoms of carbon each. So, we have 2 times N1 plus 2 times N2. Similarly, we can write a balance equation for hydrogen which would look like this: 100 times 6 equals 40 times 2 plus 6 times N1 plus 4 times N2. So, what you can see here is you have 6 atoms of hydrogen entering through 1 atom of 1 molecule of ethane, and 2 atoms of hydrogen entering through 1 molecule of hydrogen, 6 atoms of hydrogen entering through 1 molecule of leaving through 1 molecule of ethane, and 4 atoms of hydrogen leaving through 1 atom of ethylene. So, substituting all these values, you end up with 520 equals 6 N1 plus 4 N2. We now have 2 equations and 2 unknowns. These can be used to solve for N1 and N2. So, these are 2 approaches through which we can solve material balances for reactive processes. So, the first technique which we used is called as the molecular species balance. This will contain a generation or a consumption term depending on whether you are writing the balance for a reactant or a product. Once a generation or consumption term is known for one of the species, other terms can be calculated, other generation and consumption terms can be calculated using stoichiometry. One generation or consumption term has to be calculated for each independent reaction, only then we will be able to calculate the consumption and generation for each of the terms. We also can write atomic species balance, which is the second type of balances which we wrote. Here we do not have a generation or consumption term, so the equation simplifies to input equals output. Now that we have the fundamentals, let us look at this example problem. Chlorination of methane is given by the reaction methane plus chlorine giving CH3Cl plus HCl. If the feed contains 40% methane, 50% chlorine and 10% nitrogen, and 67% of the limiting reactant is converted, what is the product composition? So, now this problem uses the fundamentals and terminologies which we learnt in the previous lecture. Let us see how we can solve this problem. The first thing you see in the problem is no mass or mole flow rates have been given for the system, which means we would have to assume a basis. As the composition has been given in terms of percentages, we can use 100 moles as the basis. Why do we choose 100 moles? If you remember, I had mentioned in one of the earlier lectures that in general mass percentages are used for solids and liquids and mole percentages are used for gases. So, here the composition which is given is for a gas, which would mean the percentages that have been given are for mole percentages, and thereby we use 100 moles as the basis instead of using a mass based basis. So, let us start solving this problem. So, basis is identified as 100 moles of feed, and we know that the stoichiometric ratio of methane to chlorine is 1:1. So, based on the basis we have, we can calculate that 40 moles of methane and 50 moles of chlorine are entering into the system. So, this implies that methane is your limiting reactant, as it is provided at a lower stoichiometric amount. So, we will have to write balance equations. So, let us try to write the balance equation for the total mass and for the components. Now that we have identified methane as the limiting reactant, we can write balance equations. If we were to write the total balance equation, we would not be able to get much information, as we would have a lot of unknowns in that equation. So, instead we can start with the component balances and try to solve those equations independently. So, this particular diagram represents the process which we are looking at. So, let us write the mass balances for each of the component. So, for methane, the balance equation would look like input minus output plus generation minus consumption equals accumulation. Assuming steady state, accumulation goes to 0. Methane is actually taking part in the reaction, which means it will get consumed, it will not get generated. So, generation goes to 0, you have both input and output terms. So, this would mean that your input term, which is 40% of 100, giving you 40 moles which is coming in, minus output term for methane we have assumed to be N1, minus consumption of methane is equal to 0. Can we calculate the consumption of methane? We know that methane is the limiting reactant, and the problem statement says that 67% of the limiting reactant actually gets converted, which means consumption of methane would be 67% of 40 moles which is fed, giving you a value of 26.8 moles. So, this implies we can substitute this value for consumption and calculate the value of methane leaving the system as 13.2 moles. So, this gives you the number of moles of methane leaving the system. Now, we can write a balance equation for chlorine. So, again you would have input minus output plus generation minus consumption equals accumulation. Assuming steady state, accumulation goes to 0, chlorine is not produced in the reaction, which means generation would go to 0. So, you are only left with input, output and consumption. We know that the input term is 50 moles of chlorine entering for the basis of 100 moles, and the output is given as N2 moles, and the consumption needs to be calculated. So, what is the consumption of chlorine? That needs to be calculated. We know that for every mole of methane consumed, 1 mole of chlorine would have also been consumed. That is based on the stoichiometric ratio of methane and chlorine in the reaction. So, this means consumption of chlorine would be equal to consumption of methane, thereby giving you a value of 26.8 moles of chlorine being consumed. So, substituting it back into this equation, we will get N2 as 50 minus 26.8, giving you 23.2 moles. Now that we have calculated the outlet streams for both the reactants, we will start with the other products which are formed during this reaction and also the inert which is entering and leaving the reactor. So, now we will write a balance equation for CH3Cl. So, again we will start with input minus output plus generation minus consumption equals accumulation, accumulation goes to 0. So, this is a product, so there is no consumption, there is only generation, there is no input of CH3Cl. So, you are left with output equals generation. So, your output which is N3 is equal to generation. So, now we need to know what the generation of CH3Cl is. So, based on the stoichiometry, we know that for every mole of methane consumed, 1 mole of CH3Cl is formed, which means generation of CH3Cl would be numerically equal to consumption of methane based on stoichiometry. Thereby, generation of CH3Cl is given as 26.8 moles. So, this means we end up with N3 equals 26.8 moles. Now, we can write the balance equations for HCl. For HCl, you would again have the equation simplified to output equals generation, just like how we did for CH3Cl. So, you will have N4 equals generation. Again using stoichiometry, generation of HCl is equal to consumption of CH4 methane, which is 26.8 moles. So, this implies N4 is 26.8 moles. So, the final term which we need to calculate is the number of moles of nitrogen entering and leaving the reactor. Nitrogen does not take part in the reaction, so there should not be any generation or consumption terms, and as we do not have accumulation under steady state, the nitrogen balance becomes very simple, which is input equals output, thereby giving the output N5 as the same as input, which is 10 moles. So, with this we have calculated the number of moles of each of the components which are leaving the system. Let us now move on to another example problem. Acetobacter aceti, which is a bacteria, can convert ethanol to acetic acid under aerobic conditions. So, the reaction is given as ethanol plus oxygen forming acetic acid plus water. A continuous fermentation process for vinegar production is proposed using non-viable Acetobacter aceti cells immobilized on the surface of gelatin beads. The production target is 2 kilograms per hour of acetic acid. However, the maximum concentration of acetic acid that is tolerated by the cells is 12%. Air is pumped into the fermenter at a rate of 200 moles per hour. You are expected to calculate the minimum amount of ethanol that is required, minimum amount of water that must be used to dilute the ethanol to avoid acid inhibition, and the composition of fermenter off gas. Let us look at solving this problem. So, we have a reactor with an input that contains ethanol and water, which is called the feed stream, and you have another stream which is air. You have two different exit streams. One is the off gas, where oxygen from the air has been consumed and only the mixture of gases is leaving, and you also have another stream which is the product stream that contains acetic acid. It has been told that the amount of acetic acid which will be produced would be 2 kilograms, and it is also told that the concentration of acetic acid cannot be higher than 12%, indicating that the maximum concentration tolerated by the cells is 12%. So, that we will assume 12% acetic acid is present in the stream. Why we assume this is, in the second part of the problem we have been asked to calculate the minimum amount of water that is required for diluting the solution to get 12%. If we want minimum amount of water which is used for dilution, we would have to assume that the concentration of acetic acid would be 12%. If the concentration were to be lesser than that, the amount of water used would be more than the minimum requirement. So, for this reason we will assume the concentration of acetic acid in the product stream as 12%. Now, for performing the calculations, we need to know how much of oxygen and nitrogen are entering through the air stream. So, we know that the composition of air is given as 79% nitrogen and 21% oxygen. So, air contains 79% nitrogen and 21% oxygen. So, we have been told that 200 moles per hour of air is fed. So, this 79 and 29% are the mole percentages. So, this implies 158 moles per hour of nitrogen and 42 moles per hour of oxygen is fed into the system. So, this 158 moles per hour of nitrogen would be 158 times 28 grams of nitrogen per hour, and 42 moles of oxygen would be 42 times 32 grams per hour of oxygen. So, using this we can calculate the mass of nitrogen as mass of nitrogen is 4.424 kilograms per hour and mass of oxygen is 1.343 kilograms per hour. So, the mass of air entering the system would be the summation of these two, giving you 5.768 kilograms per hour. So, now that we have calculated the composition of air, we now have to move on to the first part of the problem, where we have been asked to calculate the minimum mass of ethanol required for producing 2 kilograms per hour of acetic acid. So, for this we will have to start with an acetic acid balance. So, if we start with the acetic acid balance, we would end up with output equals generation, because there is no input of acetic acid and obviously acetic acid is also not being consumed in this reaction, and using accumulation to be 0 for a steady state process, we end up with output equals generation, which is 2 kilograms of acetic acid being produced. Now, if this is the generation, we can also calculate the number of moles of acetic acid which is generated, so that we can use the stoichiometry. So, generation in terms of moles for acetic acid would be its mass divided by molecular weight, giving you 2 divided by 60. So, conversion to moles will give you 33.33 moles. So, 33.33 moles of acetic acid is generated during this process. Based on the stoichiometry, we know that 1 mole of ethanol which reacts forms 1 mole of acetic acid. So, to produce 33.33 moles of acetic acid, the minimum amount of ethanol which is required is also 33.33 moles. So, amount of C2H5OH required is 33.33 moles. So, to calculate mass of ethanol required, we would multiply this with its molecular weight. So, thereby we get 33.33 times 46, giving you 1.533 kilograms. Now, we move on to the next part of the problem. We have been asked to calculate the minimum amount of water that is required for diluting the acetic acid solution, so that the percentage of acetic acid does not exceed 12%. So, for this we need to perform a material balance on water. So, let us try and write a water balance equation. For that, we need to understand the composition of the product stream. The product stream contains 12% acetic acid, which means the rest 88% is water. So, the mass of the product stream P can be calculated as mass of acetic acid divided by the mass fraction of acetic acid, giving you a value of 16.67 kilograms of P, which is the acetic acid solution. If 2 kilograms of this 16.67 kilograms is acetic acid, mass of water in the product stream P would be 16.67 minus 2, giving you 14.67 kilograms leaving through the product stream. So, we need to have at least 14.67 kilograms in the product stream, so that the water dilutes acetic acid to a 12% concentration. To get 14.67 kilograms of water in the product stream, we would have to have water which is supplied through the feed. In addition to water which is fed, you also have water which is generated during the reaction. If you had looked at the reaction scheme shows that ethanol forms acetic acid and water when it reacts with oxygen. So, we have water which is also generated. So, we can account for that while we are calculating the minimum amount of water that needs to be supplied for diluting the acetic acid solution. Let us write the balance equation for water. It would look like input minus output plus generation minus consumption equals accumulation, with accumulation going to 0 for steady state process. Water is not consumed in the reaction, so consumption goes to 0. So, you are left with input minus output plus generation equals 0. So, we already know the output, so we can calculate output as input plus generation, and we know that the output is 14.67 kilograms input plus generation. So, the amount of water which should be fed would be input is 14.67 minus generation. So, we need to calculate the generation of water in this particular reaction. What is the amount of water which would be generated? If you looked at the stoichiometry, you would have seen that for every mole of acetic acid produced, 1 mole of water is also produced, which means generation of water will be equal to generation of acetic acid. So, thereby this is equal to 33.33 moles. 33.33 moles of water would have a mass of 0.33 moles would be equal to 33.33 times 18, giving you a mass of 0.6 kilograms. So, substituting it back into this equation, which is the balance equation for water, you get the mass of water which is fed W is equal to 14.67 minus 0.6, giving you 14.07 kilograms. So, we need to feed at least 14.07 kilograms of water to ensure that the product is diluted to have 12% acetic acid. For the last part of the problem, we have been asked to calculate the composition of the off gas which is leaving the system. For that, we need to write the balances for oxygen and nitrogen. So, we know that 1.34 kilograms of oxygen and 4.424 kilograms of nitrogen are entering into the system. So, let us write the oxygen balance to calculate how much oxygen has actually been consumed during this reaction. So, oxygen balance would start from again input minus output plus generation minus consumption equals accumulation. So, oxygen is not generated, it is not accumulated at steady state conditions. So, giving you input minus output minus consumption equals 0. So, you are left with calculating output as input minus consumption. We know the mass of oxygen which is input, we need to know the consumption of oxygen. How do we calculate the consumption of oxygen? Using the stoichiometry, we know that consumption of oxygen would be the same as the generation of acetic acid. For every mole of oxygen consumed, 1 mole of acetic acid is generated, which means 33.33 moles of oxygen has been consumed in the process where we have produced 33.33 moles of acetic acid. So, using this we can calculate the mass of oxygen leaving the system. So, mass of oxygen leaving the system output would be input, which is 1.344 kilograms, minus consumption, which is 33.33 moles. Converting this to mass by multiplying it with the molecular weight of 16, we would end up with, so we would end up with the mass of oxygen in the off gas as 0.277 kilograms. So, off gas contains 0.277 kilograms of oxygen. Nitrogen does not take part in the reaction, which means the nitrogen balance becomes very simple, giving input equals output. So, output of nitrogen in the off gas would be the same as the amount of nitrogen which was fed, which is 4.424 kilograms. Now that we have the masses of nitrogen and oxygen, we would have to calculate the composition of nitrogen and oxygen. So, that we can either calculate as mass fractions or mole fractions. Considering it is a gas, the more appropriate way would be to calculate these things as mole fractions. So, what we can do for that is convert the mass of oxygen and nitrogen to the moles of nitrogen and oxygen. So, moles of nitrogen in off gas is equal to, moles of nitrogen in the off gas would be equal to 158 moles, and moles of oxygen in the off gas is equal to 8.66 moles. You can perform these conversions to confirm these numbers. So, mole percentage of oxygen in off gas would be equal to 8.66 divided by 158 plus 8.66 times 100, giving you a value of 5.2%. So, the rest would be nitrogen. So, you have mole percentage of nitrogen in off gas as 94.8%. So, this gives the composition of the off gas which is leaving the system. So, right now we have actually performed two different problems to solve material balances for processes with reactions. One of the common things in both these systems were the reaction equations were given to you. In the next class we will perform one simple example problem where the stoichiometry is not given in the traditional way. We will look at a problem which has clinical applications that provides the values which are related to stoichiometry in a more common way seen in an industry or in an application rather than seen in a chemistry class. Meet you all next week. Thank you.